last time? Right, we started looking at derivatives. So derivative of a function is itself a function, is a new function, of a function f, let's say f of x, is a new function which is written f prime of x, or df dx, or dy dx. Sometimes if you're thinking of y equals f of x as a graph, the derivative of a function is a new function f prime of x, which measures the slope of the tangent line at the point x, which measures the slope of the tangent line at the point x comma y. At the point x comma f of x. Okay, so you have your function. The original function looks like this, and whatever this slope is, maybe the slope is 2. Well, here's the value of the derivative function. The derivative function there and positive there. Okay, this is what we were doing last time. You remember this? The definition. We have several ways of computing the derivative. So one way is to take, again, it's a tangent line, which is a limit of secant lines. So it's a limit as h goes to 0 of f of x plus h minus f of x divided by h. We can also compute the limit as, what do we like u's? We like u going to x, f of u minus f of x over u minus x. So this is always rise over run. This is always measuring slopes of secant lines, and the limit, the secant lines turn into tangent lines. We computed a bunch of derivatives. The derivative of the function x squared, we worked out 2x. We worked out the derivative of the function 1 over x. Anybody remember what that was? All from the definitions, negative 1 over x squared. We worked out the derivative of, did we do root x? I think we did. Anybody remember what we got for root x? 1 over 2 root x. What other derivatives did we work out? Right, we worked out the derivative of, let's say, x squared plus 1 over x. So that's complicated, right? You have to put it into this formula and do a bunch of limits, and it's a complicated function. Why, Andrew?
I don't remember when we did the math. When we did the math, we found out that.
Okay, so we proved a general theorem. We proved a general theorem, which we might call the sum. People call these rules. I don't like rules. I'll keep calling it a rule because everybody else calls it a rule. It's a shortcut. So it's not a rule like someone's, telling you go clean up your room before you can go play or something. It's not a rule like that. It's a shortcut that makes it quicker to do calculations. If you've already computed the derivative of x squared and you've already computed the derivative of 1 over x, the derivative, if I take the sum of two functions and I take that derivative, that is just the sum of the derivatives. Makes your life very easy. You don't have to recompute this derivative from scratch. You can go straight to the fact that the first derivative is 2x and the other derivative is negative 1 over x squared. And the derivative will just sum, right? You guys remember this from last time? Did we get any farther last time? We did one more thing, is we did the, what's sometimes called the constant rule. Constant rule, which is simply that the derivative of a constant is 0, which is obvious because a constant line is always flat horizontal. Okay, and I think that's as far as we got. Yeah? Okay, let's see. Let's find more rules, more shortcuts. We do not want to every single time go back to the definition because that will take a while. Now, on an exam, I might say, please compute the derivative of this function from the definition, which means I want you to set up a limit like this. Or I'll just say, what is the derivative? Compute the derivative. And that means maybe use one of the rules, one of the shortcuts that tells you what the derivative is going to be. Okay, so let's get some more shortcuts. So what happens if we have a function instead of a sum of two functions? What happens if we have a product of two functions and we try to differentiate? I don't know. Maybe it's just the product of the derivatives. That would be really nice, right? If we sum two functions and we take the derivative, it's just the sum of the derivatives. Let's test that theory by applying it to this function, d dx of x squared. Well, x squared is x times x. What's the derivative of x itself? The derivative d dx of the function x is 1, because it's a 45-degree line the whole time. So the slope is 1 times another d dx of x, which is also 1. So that's equal to 1. And yet we know that the derivative of x squared is not 1. It's 2x. So the product rule is not going to be this simple. It can't be this simple because it's just not true. We can't make up rules. The rules are shortcuts for the truth. Okay. So this is not the product rule. So this is not equal. That's not equal. And we have to work out what the product rule actually is. So let's see if we can figure out what the product rule must be. Okay. Does that make sense? The naive product rule is just not true. Lesson. So let's see. How can we figure out what the derivative of a product must be? So let's look at the derivative. We'll go back to the definition. It's the limit as u goes to x of f of u times g of u minus f of x times g of x. That's the numerator. The denominator is u minus x. Okay. Does that make sense? Everybody see why that's I'm just following the definition of derivative, applying it to not f, but f times g. How are we supposed to figure this out? Any ideas? What is multiplication? It is repeated addition. That's true. That's repeated addition if it's whole number multiplication, absolutely. But if you have, 3.14 times 2.71, whatever, what is that measuring? Something by something is measuring a area. It's measuring area, okay? So multiplication is measuring area. That gives us a suggestion that we should look at can we find a reasonable expression for this numerator that's measuring some kind of area? So if you think of this distance as f of x, okay, this distance is f of x, and maybe f of y is a little bit bigger. Let's say f of u. Let's pretend that f of u is a slightly larger quantity, okay? On this axis. On the vertical axis, I'll draw g of x will be this length as opposed to g of u, which we'll assume is this larger length. Okay, so the product f of x times g of x is this area, as opposed to the product f of u times g of u, which is this area, this whole area. You see that? So the difference between them, we want to know the difference between this big rectangle, the f of u by g of u rectangle, that area is measured by the product, and we want to subtract off the area of the f of x by g of x rectangle. Does that make sense? And so let's subdivide that region. Now, how do you want to subdivide it? We have a lot of choices for how to do it. We could divide it into 3 pieces, like this little rectangle or this little rectangle and this little rectangle, right? That's what's left over. Let me skip ahead to either. How do you want to do it? Like this? You want to do it like that? That's a reasonable way to subdivide this thing. Okay, so let's subdivide. So let's evaluate this difference. So all I'm doing is writing down a completely general identity, which is that f of u times g of u minus f of x times g of x, this is something completely general, is equal to So this big area minus this smaller area is equal to, what is this area? This area, the dimension here is f of u minus f of x is this dimension. Okay, you see that? So this is f of u minus f of x. That's this dimension. And what is this dimension? G of x times g of x. Okay, so this is one little bit of area plus another bit of area, which has this length. What's that length? This length? F of u, yep. F of u times this length. Exactly. Who said that? Tell me again. Caitlin. G of u minus g of x. Exactly, is this length. Does everybody see that? G of u minus g of x. Okay, forget about this geometry for a second. Just look at this identity. What happens when I multiply all this out? I get an f of u times g of x and a minus f of u times g of x. Those cancel. And I get a minus f of x g of x. That's right here. And I get a plus f of u g of u. That's right there. It's just an algebraic identity. How would you think to write down such an algebraic identity? Would be one way to do it, would be to look at the geometry. Okay? All we've done is written the same thing, the same numerator, we've written in a funny way. Does that make sense? Okay, so let's go with that. That's this numerator, that's the rise of this f times g derivative. The run is u minus x. And so I want to take this whole thing, I guess let me rewrite it over here. So I'm going to take this, which is f of u minus f of x times g of x plus f of u times g of u minus g of x. I'm just rewriting what's here. That's the numerator. I'm going to divide both sides by u of x. I'm going to divide both terms by u of x. And I want to take the limit as u goes to x, right? That's exactly what this derivative will be. Does everybody see that? Any questions on how I got that? Okay, so let's see if we can work out what this limit is. I see something here. So the sum of the limits is the limit of the sums, or rather the limit of the sums is the sum of each individual limit. So we can see what each term is what's happening in each term. This g of x, how does g of x change as u is changing? X is fixed, u is getting moved towards closer and closer to x. So when u is very close to x, what's happening to g of x? It never changes, right? It's just exactly. So it just stays still. So this is g of x. So this just stays g of x times what is this expression? F of u minus f of x divided by u minus x. It's the derivative of f. This is exactly the definition of the derivative of f. So all we're doing is we're taking g of x and multiplying it by the derivative of f. So that's g of x times f prime, where at the point x, f prime of x. So far, so good? Okay, and what about this other term? What's happening to f of u as u gets closer and closer to x? It's not independent of u. It has a u in it. But what happens as you get closer and closer to, as u gets closer and closer to x? F of u gets closer and closer to f of x, exactly, Sid. Okay, so this one term is turning into f of x. And what about this quotient? Let me mark these so you can see them later. This quotient is turning into that. This quotient is getting closer and closer to g prime of x. Beautiful. Everybody's getting it. That's the product rule. So the product rule, so this is the real product rule. It's not as simple as just take the product of the derivatives. It's that if you want to differentiate a product, you take the derivative of the first thing, so that's this f prime, times the actual value of the second thing, plus the value of the first times the derivative of the second. Okay, and let's see if now this new product rule gives us the correct answer in the case that we were looking at. So if we take the derivative d dx of x squared, which we think of as x times x, let's apply the product rule or shortcut, I prefer. So it's the derivative of the first thing. This says you differentiate the first thing, leave the second thing alone, just multiply it, as opposed to leave the first thing alone and multiply by the second thing. So it's the derivative of the first term, which is x, times the second term, which is x itself, plus the first term, which is x, times the derivative of the second term, which is d dx of x. What's the derivative of this? Of x is 1. This is 1. This is 1. So I have x plus x, 2x. Which is what we got from the actual definition. Okay? So we could have computed the derivative of x squared without going back to the definition, without taking limits, just by using this product rule. Does that make sense? Wait a second, we can keep going. If we can do that with x squared, let's compute the derivative of x cubed. What's the derivative of x cubed? X cubed is x squared times x. Want to try it? Try it on your own for a minute. See if you can figure it out. So you differentiate the first thing. We already know what the derivative of x squared is. And then just multiply by the second. And then add on the value of the first thing, which is x squared, times the derivative of the second. And tell me what you get. Give me a thumbs up when you got it. Okay, you guys are fast. All right, let's do it. So the derivative of the first thing is the derivative of x squared is 2x, as we already know. So that's 2x times the value of the second thing, which is just x times x, plus this complicated product rule. The first thing, which is x squared, times the derivative of the second thing. The derivative of x is. So again, the derivative of the product rule says if you take the product of two functions and you want to differentiate that product, it's the derivative of the first function times the second plus the first times the derivative of the second. Okay, that's what this computation told us. And so if we apply that in the case of x cubed is x squared times x. The derivative of x squared is 2x, and then I leave x alone. The derivative of x is 1, and I leave x squared alone. And in sum, what do I get for the derivative of x cubed? Yeah, I get a 2x squared and one more x squared, which is 3x squared. Exactly. Peter, does that make any sense? You're thinking of the power rule, which we're getting to. Yes, but we already knew that the derivative of x squared was 2x. We computed that from the definition. Okay, so that's what the 2x here turned into. I'm sorry, the x squared here turned into a 2x, leaving the x alone, the second function I left alone, plus the value of the first function times the derivative of the second function. And if I add them together, exactly, this is 2x squared, this is another x squared, that's 3x squared. And now I'm asking you to do the same thing for the function x to the fourth, which is which you can think of as x cubed times x. Okay, so so how'd you guys do it? Let me put it here so I don't forget what we did. Yeah. Okay. Quiz. The quiz is to differentiate x to the fourth, which you can think of as x cubed times x. So how'd you do it? Do we already know the derivative of x cubed? Yes, we just worked it out. The derivative of x cubed is 3x squared times the value of x itself. If you got that far, give yourself a point. Plus, other than Helen, Yusuf, x cubed, leave the first function alone, and the derivative of x is 1. So in total, so give yourself another point if you got that. And this is 3x cubed, and one more x cubed adds up to 4x cubed. Okay, great, 4x cubed. If you got that, give yourself another point. All right, pass your quizzes down. Will, sorry. Ah, brilliant. Okay. Okay, brilliant. So by the way, you could have done the same thing. Will has another idea, which is that x to the fourth is x squared times x squared. So Will's idea, Will's solution, which is perfectly fine, is that the derivative of x to the fourth is the derivative of x squared times x squared. And x squared times x squared. Okay, I know the derivative of x squared. Let me put it over here. The derivative of x squared is 2x. We already worked that out. So that's 2x times x squared plus x squared times the derivative of this x squared, which is 2x. And 2 plus 2 makes 4. So you get the same 4x cubed. Okay, great. Two ways to see the same thing. So far, so good? All right. Let's recap what we're seeing. Recap. Okay, the derivative of x. Let me do it like this. Let me go where I have some more room. Recap. Recap. Okay, the derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared, right? That's what we computed right here. The derivative of x to the fourth, is 4x cubed. This 1 is a 1 times x to the 0. What's the derivative of x to the 0? X to the 0 is 1. It's just a constant. The derivative of a constant 0 is 0 times x to the 1. The derivative of x to the negative 1, that's 1 over x. We computed the derivative of 1 over x. Negative 1 divided by x squared. Anybody see a pattern? Okay, x to the 4, x to the 3, x to the 2, x to the 1, x to the 0, x to the negative 1, x to the negative 2. The pattern continues. Wait a second. What about the derivative of square root? Where's square root? Between 1 and a half, somewhere in here, is the derivative of square root of x with respect to x, which is 1/2 x to the minus a half, which again fits exactly the same pattern. Everybody see that? All right, so that's what's called the general product power rule. So the power rule, shortcut, power rule is that the derivative of x to any power, let's say alpha, is equal to what has happened here. Yeah, whatever the power is comes down as a coefficient, and the power of x that we get is the power minus 1. Okay. We can prove this. Well, we can prove it by induction easily. Do you guys know induction? Have you heard of mathematical induction? I hate not proving things for you guys. You believe me? You believe me. All right. mathematics is anti-authoritarian. You don't trust me. That's why I have to provide you with the proof, but I'll spare you the proof. You can prove this for integers. Very easily. Should I show you the proof? Anybody want to see the proof? Okay, some people want to see the proof. Great, great. This is not a course on proofs. Okay, so the exams will not ask you to prove, things like the power rule or the product rule or the quotient rule. We want you to be able to compute these things and to understand sort of why they exist. But let me quickly show you, for example, why the power rule is true. So if you look at u to the n minus x to the n, here's a funny identity. If I take u to the n minus 1 and u to the n minus 2 times x and u to the n minus 3 times x squared, and so on, all the way up to x to the n minus 1. Let me do this with numbers. I think it'll be more illuminating. If I do u to the 5 x minus x to the 5, then u to the 4, u to the 3 times x, u squared, x cubed, and so on up to x to the 4th. Okay, you see the pattern here? The power of u goes down by 1, the power of x goes up by 1. If I multiply that by u, and I also multiply the same thing by x, and I take the difference. I'm doing this very quickly because I know some of you don't care to see it. So, but some of you do, so I want to include it for those that want to see it. What happens here? I get a u to the 5th, that's this u to the 5th. I get a plus u to the 4th x minus u to the 4th x. So this will cancel this. Everybody see that? And how about this u and times u squared x cubed? That's a u cubed x cubed. But here I get, whoops, that should be an x squared. This is what happens when you rush. Okay, so this is a u squared x squared times u gives me a u cubed x squared. But here I get a u cubed x times negative x. It's not unrelated to Pascal's triangle. It's this is more like a geometric series, but Pascal's triangle is yet another way to prove this this theorem, by the way. But yes, it's closely related. So all of the cross terms, it's called telescope. You know how a telescope, like everything folds up and all you have is the beginning. A telescope is made up of, what's a telescope look like? It's like, you can stick it out and then you can collapse it. You can collapse it all the way down so you just get the first thing and then there's the last thing. So that's what's called a telescoping sequence. When you have something that's added and subtracted, the same amount is subtracted, all that's left is the first term and the last term. Okay, so that's a general identity. And what this general identity means is if I take the limit of u to the 5 minus x to the 5 divided by u minus x, right? This whole thing is getting multiplied by u minus x. So if I take that quotient and I take the limit as u goes to x, this is the limit as u goes to x of this expression, this whole thing, which is u to the 4th plus u cubed times x plus u squared times x squared plus u times x cubed plus x to the 4th. That's the whole expression. Okay, and what happens to this as u goes to x? What happens to this term as u goes to x? This goes to x to the 4th. This goes to x to the 4th. This goes to x to the 4th. That's a times. Okay, each of the things become an x to the 4th. And how many of them are there? 5. 5x to the 4th. So the general version of this is replace 5 by n, and the same principle holds. And the same theorem holds. And of course, this is measuring the derivative of x to the 5. Okay, so that's one way to do it. You can do it using this same technique we did here. You can prove by induction that integer powers go down. What about negative integer powers? We need a reciprocal rule. What happens if you take 1 over a function? And then we can prove the reciprocal rule. So let's prove a reciprocal rule. Reciprocal rule. Anybody know the reciprocal rule? Good. They don't teach it to you as well. They should. They should teach it to you. Never mind. What's the reciprocal rule? If I know the derivative of a function, how can I figure out the derivative of 1 over a function? So let's try to figure out what the derivative of 1 over a function is. This will allow us to figure out what the negative powers are from knowing the positive powers. So is that what you're saying? Or you're telling me the answer? You're what?
I'm saying that you just make it the negative exponent.
What you're trying to do would work if we had the chain rule, which we don't have yet. We will soon. Yes. You could write this. So what you're, I'm sorry, tell me your name again. John. What John is saying is that if this f of x is 1 over f of x is f of x to the negative 1. But we can't, if we're trying to prove the product rule, we can't use the product rule to prove the product rule. And moreover, we actually need the chain rule if we want to use the product rule with this. But we can do this directly. We can do this from the definition. Okay? I already gave you a quiz, so I can't make this a quiz also. Try it. Try it on your own. See if you can compute. Take like a good 5 minutes and see if you can compute this from the definition of limits. Okay, this is a good test of your skill in manipulating the definitions. So tell me what's the first thing that I would write down? Limit, yep, as u goes to x, for example, or h goes to 0, whatever you prefer. And then the function is 1 over f of u minus 1 over f of x. That's the rise, and the run is u minus x. Okay, that's the first thing. The first thing is just to write down the definition. Now see if you can manipulate this algebraically into something that looks right. That looks something whose limit you can recognize. Take a good minute to do this. I'll try to come around. What are people trying? Anybody need a hint? Doug, what are you trying? Or you need a hint? Okay, here's a hint. We have something really complicated up here. We better simplify this in some way. We have a difference of 2 fractions. How do we simplify that? Common denominators, yep. Let's simplify this and see what happens. Anybody got it already? Okay, a couple people got it. By the way, every single thing that we're doing today is something that took humanity like 20, 30 years from Leibniz and, well, Newton, Leibniz, working out what the definitions are, how to use them, to a whole bunch of shortcuts. So this is all, it makes it seem like something you can cover in an 80-minute lecture, but these are like, each of these was a big breakthrough in the theory. So I hope you appreciate that this should be difficult. You know, just asking these kinds of questions in and of itself takes decades sometimes. Did anybody simplify the fractions? Dan, what'd you get? So it's a limit as u goes to x, bless you. Negative, okay, you did the whole thing already. Just how did you simplify this 1 over f of u minus 1 over f of x?
So I made sure they have a common denominator.
Yeah, what's the common denominator?
F of u times f of x.
Beautiful, that's a common denominator.
So then it'd be f of x minus f of u.
Beautiful.
And then
that's the numerator, and then I have to divide that by u minus x, which let me combine like this. Did anybody get this far? Just doing a little bit of algebra. Does that make sense? Okay. And what do you recognize here?
You could pull out a -1 and make it f of u minus f of x, and then they cancel u minus x.
Beautiful. So this is almost the derivative. This is almost the formula for the derivative of f. The denominator is just going to f of x and f of x. But this is almost the derivative. We're just off by a minus sign, right? This should be f of u minus f of x, and instead it's f of x minus f of u. So what Dan is saying is, if you pull out a minus sign, let me go over here. If you pull out a minus sign, this is equal to the limit as u goes to x of -1 over f of u times f of x times, now I get to switch, if I pull out a minus, I get to switch the order of these, f of u minus f of x over u minus x. Okay, what's happening to this? It's going to, exactly, it's going to the derivative of x. That's the definition of the derivative of x, is that this expression in the limit as u goes to x approaches f prime of x. What's happening here, or here rather, -1 over f of x. Yeah, both of them are, this is going to be f of x. It's just not moving as u changes. And this is getting closer and closer to f of x. So it's just f of x squared. It froze. All right, this is done. This is done. I'll bring in another thing next time. Unbelievable. Unbelievable. Nobody has an iPad. The problem is, oh, am I back? Am I back? Am I back? Okay. Okay. I'm sorry, guys. I'm not doing the iPad anymore. I'll figure something else out. Again, you find it useful to have these things recorded and have access to them. So I'll figure out something else that I can do that with. Sorry about this. Okay, the product, the reciprocal rule. This is really hard stuff. We have to be able to concentrate. We can't be bothered with this technological stuff. The reciprocal rule, we're trying to compute the derivative of 1 over x, 1 over f of 1 over some function, right? We went to the definition, we did a bit of algebra, we manipulated things until we saw something that's turning into the derivative of f, and something else that's -1 times f squared. So that is the reciprocal rule, that if you want to take 1 over a function and differentiate it, that's equal to negative the derivative of the function divided by the function squared. And if we have the reciprocal rule, then we can chain that with the product rule. Where was our power rule, rather? If we put that together with the power rule, we'll get the negative. We'll be able to prove all the negative powers do what they're supposed to. Let's see why that's the case. So what is the derivative, d dx, of x to the minus n? In other words, 1 over x to the n. Well, if we use the reciprocal rule, that's minus the derivative of x to the n. What's the derivative of x to the n? N times x to the n minus 1. Am I hearing something? Sorry. Right, this derivative divided by f of x squared. F of x is x to the n, so that's x to the 2n. Everybody see that? So this is the derivative of the function x to the n divided by the function x to the n squared, which is x to the 2n. All right, and let's simplify that. I get -n times x to what power? Here I have an n minus 1, and here I have a 2n in the denominator. So what power do I get? Up here? 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 Here. X to the minus n. x to the minus n is 1 over x to the n. So the function that I'm thinking of is the function x to the n. The function is x to the n. Oh, it looks like an h. I'm sorry. That is an n. And yeah, thanks, Will. Okay. So what is the power that we get when we, so I pulled out the minus n, that's just a constant. I have an x to the n minus 1 on top and an x to the 2n on bottom. That makes a total of x to the, other than Raghav, other than Halan, other than Rahan. I have an n minus 1 minus 2n. Janani? Negative n minus 1. Negative n minus 1. There's a plus n and a minus 2n, so that gives us a minus n, and then there's a minus 1. And look at what that is. That's whatever the exponent was, that exponent came down, and we got 1 less in the exponent. So the power rule continues to hold even on the negative numbers. Okay? If you want to get the power rule to hold for all numbers, there's a variety of ways of doing this. Actually, my preferred way is Newton's binomial theorem, which is a topic outside of our, I'll post a video that discusses Newton's binomial theorem. You can look at that. Okay, so we have the reciprocal rule. Let's summarize some of our rules. Rule summary, rule roundup. Rule roundup. What rules do we know so far? The power rule, right? One at a time. Power rule, the derivative of x to any power is that power comes down and the exponent is 1 less. We have a product rule. A product rule, the derivative of the product of two things is equal to the product of the derivatives. No, it's not the product of the derivatives. It's, what is it? The derivative of the first thing times the second plus the second, g prime times f, yeah, or f times g prime, whatever you prefer. The product rule. We have a reciprocal rule. I'll tell you why people don't know the reciprocal rule off the top of their head, because you can combine the product and reciprocal rule into one, which we'll do in a second, which is, sorry? Oh, is the question? No. The reciprocal rule, the derivative of 1 over a function is this, negative the derivative divided by the function squared. And now let's combine those together into one, which is, I heard somebody say, the quotient rule, the quotient. So the quotient shortcut or rule is what happens when you divide two functions. If I have f divided by g and I take that derivative, what happens to that? Okay. Well, we know what happens to the product of two functions, and we know what happens if we take the reciprocal of a function. So it's actually very easy to chain these two rules together, combine them together to get the answer here. So that's the function f times the function 1 over g. If we only had a rule that told us what happens to the product of two functions, the product rule, thank you. The product rule says we differentiate the first function, leave the second function alone, plus differentiate, leave the first function alone, and differentiate the second function. But if we only had some rule that told us what to do with the derivative of the reciprocal rule, right? So this is, let's write it as f prime over g plus f times, and I just lost my reciprocal rule. There's my reciprocal rule, plus f times, let's see, it's negative g prime divided by g squared. Right? The reciprocal rule says you put the negative derivative in the numerator and square the denominator. Everybody see that? Great. Okay. Let's massage this a little bit. What's the common denominator going to be? g squared. So let me multiply top and bottom here by g. So I have f prime times g, common denominator is g squared. And then I have a minus f times g prime. That's it. That is the dreaded or beloved, depending on your opinion of this rule, that's the quotient rule. The quotient rule is that this is the derivative. This is the derivative of f divided by g. Cool. People, I don't like to memorize things. I like to use things a lot. And so you just get used to it. But people have songs, I'm told, that they memorize this with. What is it? I remember last time I had never heard of these songs. And then my students told me there were songs. And now I don't remember what they were. But some of you must know. Row, row, row your boat. What low is the bottom and high is the top, right? And what is it? Low D high, low D high, D high meaning the derivative of the top, low D high minus high D low. And over the square of what's below. Over the square of what's below. Okay, let's low D high minus high D low over the square of what's below? Over the square of what's below. I think I heard low D high minus high D low, square the bottom and away you go. I mean, there's all kinds of variations on it. This one's better. Fine. Yeah. This one will get you the A. The other one's crap. Yeah. That's for 135. Yeah, that's not 151 material. Right. So low D high minus high. Let's not disparage the 135. They're working very hard. Low D high minus high D low over the square of what's below. Okay. Whatever works for you. This is now part of your toolkit, and you can solve all kinds of things using this identity. Do you guys remember last time we computed the derivative of something like x over x minus 1 dx from the definition? And I did something off to the side to check if the answer we got was right. You know what I did? The quotient rule. So let's do it together now, instead of me hiding it from you. So low is, you want to take a minute and do it by yourself using the quotient rule? Take a minute. Let's not forget the song here. Low D high minus high D low over the square of what's below. I have no objections to your desire for this one over the other one, or any other. I'm sure there are more songs like this. No, but this one's the best. You're right. You're right. I'm sorry. This is the best song. Best song. Okay. All of the songs are forbidden. If you even try to write another song on the exam, you get a 0 for the exam. This is the one. Okay. I will be grading the songs, yes. Yeah. As well as the quality of the pitch and what key you start on. I'll talk to the music department. Yeah, maybe they'll transfer. Did anybody get this? Other than Raga, do you have a question or you have the answer? I know you have the answer. No, but Janani. Okay, wait. Let's do it together. So what did you start with? Low is x minus 1. D high by 1. The derivative of x is 1 minus high is x. D low. The derivative of x minus 1 is 1. How did you know that without doing anything? You can use the power rule. Yeah, you can do it a variety of ways. First of all, you can think of it as x minus 1 is just a 45-degree line, just not through the origin. Who cares where it is? It's still at the same slope. The slope is indeed 1. You can also use the sum rule. We know the derivative of x, and we know the derivative of a constant is 0, so we can add, right? So there's a variety of ways you could have worked out what the derivative of x minus 1 is. So that's low d high minus high d low over the square of what's below, and what's below is x minus 1. It is the best song. It's undoubtable. Cannot be debated. Anything in this class can be debated, not whether this is the best song. Okay? Just for the record. All right. So I get an x minus an x and a negative 1. So I get a negative 1 over x minus 1 squared. And hopefully that is what we got last time the long way, meaning from the definition. That's why these are shortcuts, right? These rules, they're shortcuts. They make your life easier. Good? Let's do another. Well, this is an internal quiz, not to be handed in. Let's see how you do with the derivative of 4x squared plus x minus 7 divided by x cubed plus 13. Whoa. Can you imagine how long it would take for us to figure this out if we were using the limit definition? U going to x and so on. Shortcuts. Shortcuts. You are more than welcome to practice your limits and see if you can see why this thing converges to what it does using the definition. But now I give you the full power of everything that we just developed. Mathematics is about laziness in some sense, but a good kind of laziness. Work really hard so that you can be very lazy. Okay? So we did all that work that will now make this computation extremely easy. And let me make sure you can see the quotient rule so that you can apply it in action. Tell me, give me a thumbs up when you got this. No. In other words, don't do the algebra once you're at the. Is that a 13 or a B? That is a 13. B equals 13. Give me a thumbs up when you got it. Anybody not even know where to start? Anybody want help just getting the first steps? Okay. Everybody's hard at work, or is everybody done? Don't multiply out. Yeah, it's going to be some complicated algebra. Don't multiply out the numerator. Everybody got it? Annabelle, you're still working? You're just looking at it? You're just in awe of its ugliness? Or you're done?
I'm done.
Oh, you're done. You're just staring at it. You're just staring into space because you're done and bored. Okay, let's do it together. So, our song is low, low, D high. How are we going to differentiate this numerator? We have a sum of constants times times things. Did we talk about the constant multiplying rule? Oh, I missed one. Okay, sorry. So this is a consequence of the product rule. Let's apply the product rule to when one of the functions is a constant. So if I have a constant times some function and I want to differentiate that, if I apply the product rule, that says it's the derivative of the constant times f plus the constant times the function. What is the derivative of a constant? 0. So this term isn't there. Okay, so if you want to differentiate a constant, the constant just pulls out of the derivative, right? If whatever your slope is, you multiply everything by a factor of 10, your slope will also multiply by a factor of 10. Does that make sense? Okay, so we have a constant 4 in front of a function x squared that we know. So the derivative of that will be 4 times the derivative of x squared. The 2 comes down and the exponent gets decremented by 1. So I get 2 times x to the 1 plus the derivative of x is 1 plus the derivative of negative 7 is 0. Okay, so that's low, d high, minus high is just copy it down, d low. So d low, the derivative of x cubed using the power rule is 3x squared plus, well, I don't have to write plus zeros every time. You know the derivatives of constants are 0. The song is over the square of what's below. Over the square of what's below, which is x cubed plus 13. Done. Right? This is why these rules make our lives easier. We did all the hard work using the definitions. I might still ask you to do something using a definition that won't be anywhere near this complicated, but now you can do all kinds of things just using the definition. All right, let's do a couple more of these. Oh, there's one other thing that I want to say, which is you can also repeatedly differentiate. So when you have a function, so one more topic that I have to tell you for your homework is repeated differentiation. Repeated differentiation. So you can look at the first derivative of a function. You can look at the second derivative of a function. So this is a second derivative. Second derivative. Also called f double prime. F double prime. Also called the d squared dx squared of f, or d squared y over dx squared. This always confused me. Why does the square come here? Why isn't it dy squared over dx squared? I just never liked this notation, but it's because you're applying the operator ddx twice. Can you write all the notation for delta? Some people will write like a d squared f for derivative. Well, delta has a particular meaning, the Laplace Beltrami operator. We're not going to talk about that here. So let's see some examples. What is the second derivative? Let's see, we just worked this out. X over x minus 1 double prime. What's the second derivative of x over x minus 1? Well, the first derivative we just worked out. What was the first derivative? Anybody remember? Yeah, negative 1 over x minus 1 squared. So this is negative 1 over x minus 1 squared. So we want to differentiate that again to get the second derivative. So let's do that. You guys want to do it on your own for a second? Or should we just all do it together? Yeah, just do it together. Okay. What do you want to use for this? The sum? Is that what I heard? In other words, the quotient rule. It's no longer called the quotient rule. It is now called the sum. That's a decree. So let's use the sum. Low, d high, minus high is negative 1. Sorry, low, d high. The derivative of negative 1 is indeed 0. We have an x minus 1 squared that we're going to have to differentiate. We don't know the chain rule yet. We have an x minus 1 squared. It's not hard to differentiate x minus 1 squared by just working out what x minus 1 squared is. It's x squared minus 2x plus 1. Okay, so that's what the denominator is. So it's low d high. I mean, the high is a constant. We really would rather use the reciprocal rule. That's even better. Raga. How did we derive the reciprocal rule? We can absolutely do this using the reciprocal rule. In fact, the reciprocal rule now is a special case of the song rule. What do we call it? The best song. The reciprocal rule is now a special case of the song rule, precisely as we're seeing here.